Hey guys, welcome to the next lesson. And today we're going to talk about a confidence interval for beta. So we've been estimating alpha, we've been estimating beta, and we've been estimating sigma. But by far the most important of those is beta. That's the true slope of the true regression line. And we like to estimate it based on a sample. So we're going to do that by using a confidence interval. So here our parameter is beta. Our statistic that estimates beta is B. And everybody in class, so we have 25 different values of B. So I collected all the values of B that you gave me. And this is what they look like as a distribution. No surprise, everybody has a different sample of 12 players. So everybody has a different slope of their regression line. But it looks like it's starting to take on a shape that looks somewhat symmetric and perhaps even normal. Now we've only done 25 Bs here, but if we did a lot more, then it would really take shape. Now, of course, the true sampling distribution only happens if we get every single possible sample of 12 players from that list and find the regression line for all of those. And that would take, of course, forever. But if we did it, perhaps that sampling distribution could be modeled with a normal curve. That's our hope, right? So under certain conditions, perhaps that will happen. And of course, that normal distribution would be centered at the parameter beta. And our sampling distribution would have a standard deviation, which we can add to the picture here. So if we went one standard deviation up, this would be standard deviation of our B's. Again, that's our statistic here. So it's a standard deviation of all our B's would be equal to this, if that's one standard deviation up. And it turns out there's a formula for that. And the formula for the standard deviation of your statistic, in this case, the standard deviation of your B's, is going to be equal to this. Sigma, that's the numerator. And remember what that is. That's the prediction error when you're using the true regression line, right? S estimates that. And then we have the standard deviation of X. So what that is just the standard deviation of your X data. So for us, that would be the standard deviation of shots taken, right? And times the square root of the sample size, n. Now, what we're looking at there in that formula is a formula that we'll never, ever use, right? Because it involves two standard deviations, and we're not going to know either one of those because they both require the entire population, right? That's the prediction error for all 162 players. If we found the regression line for all 162 players, it would be this. This would be the standard deviation of shots taken for all 162 players. So that's population numbers we're never going to get those values, but we can estimate this, as we know, with S, and we can estimate this as well, the standard deviation of the 162 players for shots taken. That's our X variable. We can estimate that with S of X. Okay, but of course, when we do that, we're going to get an estimate for what we really want. So the standard deviation of the B's is what we want. We'll estimate it with what we're going to call the standard error of the B's. So that's what we're going to do next. So we can estimate this with, like I said, the standard error of B. So we're going to replace or estimate sigma with S. We'll estimate the standard deviation of the X values with the standard deviation of the 12 X values in our sample. And then we'll multiply by the square root of n minus 1 instead of the square root of n. So in order to calculate this, we're going to need the calculator's help. Now, we already know from the previous lesson that the value of S, we said was about 2.0, but we'll get a more accurate number for that. We'll go maybe 4 decimal places in. It'll be 1.99 something, I think. We'll also need to calculate this, the standard deviation of our X variable, shots taken per game, so we want to find that. And of course, we know our sample size. We sampled 12. And we're going to use my sample, the one that we were looking at yesterday, to do our calculations. So let's do that. Let's jump into the calculator and see what we come up with. Okay, so in order to find our standard error of B's, we need S of X. Remember S, that's your prediction error. It's the sum of your squared residuals divided by n minus 2. Don't forget the square root, which I forgot yesterday. So let's do that. Hopefully you still have the data for this sample, so my sample, in L5 and L6. So there it is. There's the data. So what we're going to do is find all the residuals. Now, I can't just highlight L2 and put the residuals in there because the residuals in the calculator right now are whatever the residuals were the last time we executed a regression. So let's execute the regression. So stat calculate, choice 8. So in this random sample of 12 players, the explanatory variable, shots taken per game, so that's an L5. Points per game, that's an L6 for this random sample of 12. I don't think I need to store the equation, so I'll just hit enter for calculate. And okay, so I've performed the regression. So now the residuals we want are in that list called resid. So we go back to the list editor, so stat edit, and let's just put them in L2. So we'll highlight L2, we'll hit enter, and second list, and resid, so find that resid list, and these are the residuals. As we know, if we added them up, we would get 0. That's why we're going to square them all. So we highlight L3, hit enter, and we want to square everything in L2, so L2 squared. So these are the squared residuals. I want the sum of all of those guys, so I'll hit second quit. If I hit second list, which is above stat, I can now find the sum. It's in the math menu, it's choice 5. We want the sum of all those squared residuals that are in L3, and we get this. We want to divide this by n minus 2. Well, our sample size is 12. We sampled 12 players, or I sampled 12 players. So n is 12. So we're going to divide by 12 minus 2. We're going to divide by 10. So you divide this number by 10. You get this. Yesterday we said this is about 4. The square root is going to be 2.0-ish. So that's the number we used yesterday. But let's actually take the square root of this number. So square root of answer, I guess. Okay. And the square root of this number, this is our value of s. So we said it was 2.0 yesterday, so to the nearest tenth, that's what it is. But let's go 4 decimal places in. It looks like 1.9919. So we'll say s, our value of s, is 1.9919. 1.9919 to 4 decimal places. All right. Now we need the standard deviation of the x variable. So remember, the x variable are the shots taken. So if I hit stat edit, where are the shots taken per game? Well, that's right here in L5, right? So these are the shots taken per game for each of these players. So they're all there in L5. So we're going to find the standard deviation of that sample of shots taken. So we go to one variable stat. So we hit stat calculate, and we do one variable stats for, well, it's already in there, L5. So we're going to do this calculation. By the way, in our sample, the average number of shots taken is 12.25. But what we want here is the standard deviation, which is this number right here, S sub x, so 4.0923. So this looks like it's 4.0923. And of course, we know n, that's 12. So we have all 3 pieces we need to calculate the standard error of b. So let's go back to the board and find it. Okay, slight correction. I had said 4.0923 in the video, but it's 4.0927. You might have noticed that. Okay, so we have the values we need. Let's figure out what the standard error of b is. Again, it's an estimate for the standard deviation of our sampling distribution. So we just plug in the numbers. So 1.9919 divided by the standard deviation of x, which is this, 4.0927, times the square root of n minus 1. Well, we're sampling 12 players, so n minus 1 would be 11. So times the square root of 11. All right, so we take out the trusty calculator and we do it. So double check me on this. Make sure I'm getting the right number here. 1.9919 divided by 4.0927 times the square root of 11. And it looks like I'm getting 0.1467. We'll just call it 0.147. So the standard error of b is 0.147, and that's a value that we're going to need as we move forward, because it's going to be a big part of our confidence interval. Speaking of the confidence interval, let's get into it. All right, so we want to do this confidence interval for beta, and we're using our value of b, which by the way for my sample was 1.51. And when we get that 1.51 for b, we're not saying that beta is 1.51. We want to catch beta in our net by building a confidence interval around my estimate, right? So that's the point of the confidence interval. We're going to build a net around my 1.51 value of b. Okay, but every confidence interval has the same structure, right? It's always your statistic, that's your estimate for your parameter, plus or minus your margin of error. But your margin of error is made up of 2 components. One of those, the first one, is the critical value. And then times the standard deviation of the statistic if you have it. This is the standard deviation of our statistic, but remember we can't do that. That's why we estimate it with the standard error of B. So usually this is a standard error of the statistic, not a standard deviation. So for us, this is actually going to be a standard error because we have to estimate this guy with our standard error of B, which is that value we just found. Okay, so in an ideal world, though, we would do our statistic. We know the statistic that estimates beta is B, plus or minus. In an ideal world, this would be a Z star critical value times the standard deviation of the statistic, sigma B. But as we just said, we're not going to be able to get this, so we're going to estimate it with a standard error. So this becomes B plus or minus, and we're going to replace this with a standard error. But in the process of doing so, our critical value won't be a critical Z, it'll be a critical T value. So this will be a T star times the standard error of B. And this is our formula for finding a confidence interval for the slope or for beta. So it's going to be B plus or minus this, T star times the standard error of B. So that'll be the size of the net that we build around our value of B. Okay, so we're going to do all the steps for a confidence interval. You might remember these, D, N, C, I, S. So D is to define the parameter and state the confidence level. And let's use a 90% confidence level today. So we'll use 90%. So let's do it. We're going to say, let's estimate beta, the true slope of the true regression line. So let's estimate beta. And we'll do it with 90% confidence. So there you are stating the confidence level. We're going to use 90%. So let's estimate beta with 90% confidence. And of course, now we have to define the parameter, define beta. So where beta is, and we'll define it this way, the slope of the true regression line. Now, of course, when we write this, the slope of the true regression line, we're not going to stop there because what is missing here is context. And of course, we need that context. So beta is the slope of the true regression line, which predicts points scored per game So it predicts points scored per game based on number of shots per game. And we also have to make it clear that we're talking about a parameter here. We're talking about the population of all 162 NBA players. So based on the number of shots per game for all 162 NBA players. By the way, there are more than 162 NBA players, but our list consists of the 162 players who take at least 8 shots a game. So that's technically not the entire league right there, but that's the population. So we have done step 1, which is to define the parameter in the confidence interval and mention the confidence level. So the next step is going to be to name the interval, and then we're going to check the conditions, and then we'll find the interval, and then state our conclusion. And that's all coming your way next. Okay, so we are now ready to name the interval and then check the conditions. So we say if conditions are met, we'll find and there's the name of it, a 1 sample T interval for beta. So we've named the test. Now we're going to check all of those conditions. And as we've seen, there's really 5 things to look at with our acronym LINER. So the first, of course, up is L. So we want to see if a linear model is appropriate. How do we know if a linear model is appropriate? Well, we want to look at the residual plot, and we're hoping to see the lack of a pattern. Okay, so we're going to need the calculator's help to see that residual plot. So let's jump into the calculator and take a look at it now. Okay, so we'd like to get our residual plot. And this is our original data here in L5 and L6. We actually have the residuals right here in L2, right? Because we were finding those on our way to finding S before when we squared all the residuals. So our residuals are actually right here in L2. So we'll make our residual plot. In a residual plot, of course, the vertical axis or the y-axis is your residuals. The x-axis could be a couple of different things, but usually we'll go with the simplest thing, and that's our original x values, which are here in L5. So let's take a look at the residual plot. So we hit second stat plot, and we'll turn that on. Looks like it is on. We'll choose the plot with the dots, and we want the x list to be our original x list, so our shots taken, which are in L5. And you could put resid here, or since the residuals are in list 2, you can just choose L2. All right, we'll hit zoom 9, and we'll see our residual plot. Okay, so the residual plot looks like this. I definitely don't see any distinct pattern here, which is good news. So what this means is a linear model is appropriate. But we do need to copy a picture of this into our work to show the reader of our work that we're actually looking at it. So let's do that now. Okay, so we want to show that we're looking at the residual plot. So you copy down a rough picture of what it is. So we have shots per game here. Notice I labeled the numbers here. You might not really have to do that. But at minimum, maybe shots per game, residuals here. And just a general gist for what the residual plot looks like. As we noted, there was no pattern, distinct pattern in the scatter plot, or sorry, in the residual plot, that is. So since there's no pattern in the residual plot, we're going to say a linear model is appropriate. So we'll write that. So since there is no distinct pattern, we're going to say no pattern, I guess. So since there's no pattern in the residual plot, we can comfortably say that a linear model is appropriate. All right, so we now know a linear model is appropriate thanks to the lack of a pattern in our residual plot. Now we're going to need that residual plot later, as we know, for one of the other conditions. So I is independent, and that's independent observations within your sample. So we sampled 12 players, and we did it without replacement, right? We're not going to choose the same player twice. So is the sample size small enough relative to the population to get us this pseudo-independence that we want? I think it is, but we're going to check it with our 10% condition. So we check the 10% condition here. Is the sample size less than or equal to 1/10 of the population size? Our sample size was 12. Our population size is 162 players. That's our population. And 12 is indeed less than or equal to 16.2. So this condition is met. The next condition is the N condition to our liner, L-I-N-E-R. That stands for normal. Now, technically, what we want is normality at each X value. And actually, from the residual plot, we can see we only have 3 players with 8 shots a game, 2 with 9, 1 with 10. It looks like maybe none with 11, maybe 1 with 12, none with 13, none with 14. So clearly, we're not going to be able to tell whether we have a normal distribution of Y values at each X. That's why we pool them all together and look at them as a group. And of course, what we're looking at are the residuals themselves. And we want to see, are the residuals normally distributed, right? So we need a picture of a histogram of our residuals. So we'll use our calculator to help us with that. So let's get back into the calculator and do it. Okay, so since we don't have enough data points at each X to see if we have a normal distribution around that particular X value, we're going to put all of the residuals together and see if we have a normal distribution. Maybe not exactly normal, but at least symmetric without any severe skew. So we want to take a look at a histogram of all of our residuals. So we have all the residuals right here in L2. So let's do this. So we'll hit second stat plot. We want to take a look at a histogram. So we choose the histogram here. And we want to do a histogram of the residuals. So if you have the residuals in resid, in other words, if the most recent execution of your regression analysis was done on this data, for this random group of 12 basketball players, then you can use resid here. But we know we have the residuals in L2, right? So I'm just going to put L2 in there. And this will give us the histogram of the residuals. And we're hoping for lack of skew and symmetry. Let's see what we see. Okay, so let's get rid of that line, actually. I don't want to see that. I'll get rid of both of these lines, actually. All right. So, okay, so this doesn't look so good, does it? Right? We see a definite severe right skew, but histograms are funny, right? If you change the size, the class size, or the bin size, you can dramatically alter the shape. So what I'm going to do here is I'm going to go to my window and I'm going to just go down to -5 and up to +5. And I'll use an X scale of 1. So I'm using a bin size of 1 here, and I'm going from -5 to 5. And it'll change the appearance of the histogram a little bit. So now it looks like this. And yeah, although it still has that slight right skew, I think it's kind of a forgivable right skew. So I'm going to say, okay, it's feasible this was drawn from a normal population perhaps. So I'm going to say this condition is met. And keep in mind, it doesn't matter what your conclusion actually is. If you go with that original histogram and say it's severely right skewed, conditions not met, then you would just say, I'm going to proceed with caution. But if you get a histogram, it's the same data, and you change the bin size, and it looks like this, okay, this is good enough. So I'm going to say condition is met. All right, so we need to duplicate this graph onto our board. So let's do that now. All right, so we want to duplicate that histogram that we saw in the calculator for our residuals. So I redrew the picture here, and let's say, okay, I'm looking at this picture. And since we have, rough symmetry here, I'm going to say the condition is met as a result. So since the distribution of residuals is roughly symmetric, I'm going to add this detail here. I'm going to say and single peak. That's actually relatively important, right? Because we could have a distribution that's symmetric, but it's like uniform, right? So we don't really want to see that, right? We want to see single peaked and symmetric. So that's why I added that there. So that's a nice phrase to add to this. So since the distribution of residuals is roughly symmetric and single peaked, the condition is met. Okay, so now we're ready to check the E for our liner. Remember, this stands for equal variances. And we're going to use the residual plot to check this. So remember, we want equal variation or equal variance at each x value. Not exactly the same, but roughly the same. So do we have that here? And I'm not so sure, right? So again, to check this condition, we go back to the residual plot. It looks like, based on this residual plot, that we're seeing a little bit more variation as the number of shots per game goes up, right? We don't have as much variation here as we do here. So I'm going to say this condition fails for that reason. So I'm going to say since the variation increases as the number of shots per game increase, this condition fails. And remember, when we're looking at this condition, we're not looking for perfect equivalent variance across the board, but roughly. And here, I'm not so sure we have that. I don't think we can say we even have roughly equal variance. It looks like the variance increases as the number of shots increase. So since I'm going with a condition failing here, so we add the weasel words, we'll proceed with caution, because I'm not 100% sure this condition is actually met. Our final condition that is R, random, and that is met, right? The 12 players were selected randomly. So the 12 players were selected randomly. So I chose this set of 12 just like you did, using the calculator, doing it randomly. So the 12 players were selected randomly. Okay, so because one of these conditions failed, we're going to proceed anyway, but we're going to say we're going to proceed with caution. Because again, I'm not so sure I'm seeing that equal variance that I'd want to see in my residual plot. Okay, so we've defined the parameter that we're trying to estimate, which is beta, and stated the confidence level. We named the interval. We just checked the conditions. So now it's time to find the interval, and that's coming your way next. Okay, so now comes the time to find our confidence interval. We will need this number. Remember, we went through those calculations before. But there's good news about this. We're typically not going to have to go through those calculations we did before to get this. So at the end of the video, I'm going to show you how we're going to get our hands on this number. It's going to be a much easier way than what we did here. So we don't have to worry about memorizing formulas like this. But we do have to know the structure of our confidence interval. Just a reminder, we said we were going to do a 90% confidence level. So our confidence level C is 90%. And so just a reminder of that. But the structure is this. That's our statistic B plus or minus our critical value, which is going to be a T-star value, times the standard error of B, which is an estimate for the standard deviation of B. That's this number right here. So I have this. Remember, our B, or my B for my sample, was 1.51. So that was my 1.51. That's the number we're going to build our net around. We have this. And now what do we need? We need the critical T for 90% confidence. So I need the critical T for 90% confidence. And for linear regression inference, the number of degrees of freedom, and I didn't mention this before, so write it down now. The degrees of freedom is n minus 2. You might want to put a star there because I meant to write it when we were presenting the structure of this originally, but I forgot to mention it. So degrees of freedom is going to be n minus 2 for this. So 90% and degrees of freedom 10, and we have to find this value. So let's refresh our memories on how we do this. We had two ways of doing it, one with the table, one with the calculator. So let me show you both of those one more time, coming your way next. Okay, so we need a critical T, specifically a critical T with 90% confidence and 10 degrees of freedom. And we're going to do it both ways, the calculator and the table. By far the easier way is with the table, because all you got to do is find that 90% number in the bottom row here, and then go up to your 10 degrees of freedom. And there it is, 1.812. So we see that our critical T is going to be 1.812. Very easy to find using your T table. Again, 90% at the bottom. You just go up to the 10 degrees of freedom. There it is. Okay, how do you get there with the calculator? Well, you have to hit second distributions, which is above ours, and then inverse T, which is choice 4. Now, the area is not going to be 90%. Right? Because it's going to be 95%, so it's 90% in the middle, but we want to have that value that has 95% to its left. So remember that picture in your head. I'm not going to redraw it again. So you have to put 0.95 in here. So as you can see, it's trickier with the calculator. 10 degrees of freedom. And we hit enter, and there it is, 1.812. Okay, so we have all the pieces we need for our confidence interval. So I'll just rewrite the formula, right? It's formula and then plugins. So we have B plus or minus T star times the standard error of B. So the B in my sample, my slope I found was 1.51. We're now going to build a net around it with our margin of error, which is made up of these two things. So T star, 1.812. The standard error of B, 0.147. All right, so 1.51. What I like to do is just multiply these two numbers together because that gives us the margin of error. So 1.812 times 0.147, and we get 0.266-ish. In fact, I'll just call it 0.27 just for simplicity's sake. That's your margin of error. So that's the size of our net to the right and to the left. So if we do 1.51 minus this number and 1.51 plus this number, we're going to get the confidence interval from 1.24 up to, and then when you add these, I guess 1.78. So there's the calculation of our interval. So we've done this step. And now, of course, we need to state our conclusion. Okay, so we're going to state our conclusion right now. Before we do, let's talk about this for a second. So what we're saying is we don't know what the true slope is for the true regression line, but we're 90% confident that it's a number on this list, 1.24, 1.25, 1.26, all the way down to 1.78. So I don't know what the true slope is for the true regression line, but it's some number on this list. At least I'm 90% confident that it is. So I'm 90% sure it's going to be a number on this list somewhere, anywhere on this list. Okay, so we write our conclusion here. We say we are 90% confident. Remember, that was our confidence level, 90%. So we are 90% confident. And when we write this conclusion, instead of saying we're 90% confident that the true slope of the true regression line is between those numbers, let's see if we can incorporate the meaning of what slope really is, right? So really the slope is for each additional shot taken, it's the predicted number of points, of extra points you're going to get from that one additional shot, right? So let's write it in that reference frame. So we're going to say we are 90% confident that an NBA player's scoring output, so an NBA player's scoring output will increase. So will increase by, and we'll say will increase by an amount between 1.24 and 1.78. So 1.24 and 1.78 points. For each additional shot taken. So for each one shot. So for each additional shot taken. And of course, what we're saying here is on average. So for each additional shot an NBA player takes, we're saying that they're going to score an extra somewhere between 1.24 and 1.78 points for each additional shot on average. Okay, so finally what I'd like to show you, actually no, before we get there, this is important too. Notice in our interval, we don't have the number 0 in there, right? And that's important because what we're saying is, yeah, we're pretty sure that there's a positive association here, right? Because we don't have 0 as a potential value in this confidence interval, right? So we're going to say since 0 is not in the interval. So this is a nice thing to say too. We're going to say since 0 is not in the interval, it's basically saying that we're really confident that the slope is positive. So we're confident that we have a positive association. So since 0 is not in the interval, and we can even add to that, and all plausible values are positive. In fact, we need to add that part. And all plausible values are positive. So that's important, actually. We actually definitely need to say that part. We can say we are confident that a positive linear relationship exists here. So we are confident that a positive linear relationship exists. Between shots taken, or we'll just say shots per game and points per game. Zero is not in the interval. These are all positive. So we're pretty sure that whatever that true slope is, it's a positive number. Therefore, we're pretty sure we have a positive association here. Now what I want to get to is, we saw how tedious it was to calculate that value of the standard error of B. So I'm going to show you the way we typically get it, which I said before is much easier, and that's coming your way next. Okay, so as I said before, there's a much easier way to get our hands on the values that we need for this. Now the t-star we saw very easy to find with the table, or you can use the calculator if you choose. So 1.812. B, of course, is the slope of our regression line in our sample, and we've seen this before in the computer output. That's going to be this number right here, right? So 1.5064. So we can say it's 1.5064. We used the rounded 1.51 when we did it. But if you don't want to round the number, there it is, 1.5064 right there. That's the coefficient to shots per game. And then the other number. This is the one where we did those tedious calculations for. That was the standard error of B. But first, let's fill in our T-star, 1.812. Again, that's easy to find from the table or the calculator. But now the standard error of B. Well, notice this is the slope. This is the standard error of that slope. There it is, 0.1467. When we calculated it, we said it was 0.147, I guess, right? So there it is, all the numbers you need for your confidence interval. And this is typically the way we do it. We don't want to get wrapped up in tedious calculations or memorizing formulas. So usually for problems like this, we just go right to the computer output. Again, there's your slope. There's the standard error of your slope. And as we know, there's our S, there's our R square. And tomorrow we're going to see that this is going to be useful too. Notice that's not the critical T, but that's going to be a t-test statistic. And we'll take a close look at that tomorrow. And that's going to be the associated p-value that goes along with it. But again, the computer output, that's typically the way we do these things. So make sure you're good at reading the computer output to find the values you need.